Hey class, so I think problem 54 might be a little bit tricky, even though I told you I was giving you guys homework that wasn't too tricky. I realize all the different things that need to come together might be a little confusing on this one, although this is an excellent problem to really throw multiple concepts that we've been learning lately together into one problem. So what we have going on here, as you hopefully know by now, is we're having an electron that's being launched into a solenoid. But we're told that it's being launched at a 32-degree angle relative to the central axis of the solenoid. So I tried to represent that here, and you can kind of see, if you imagine, this is the central axis, then that means this angle here is the 32-degree angle. And so what that means is the velocity has both a perpendicular component of velocity, which would be v times the sine of that angle theta, and a parallel component of the velocity, which would be equal to v times the cosine of the angle theta. So what does that mean? Well, it means that the electron, as it's moving down, is going to have a helical path. The parallel component of the velocity is going to keep it moving down the straight center of the, moving in a horizontal direction down the solenoid, and the perpendicular component, as it enters the B field, since the velocity is perpendicular to the B field, it will experience a force that will cause it to go through rotation. So it's going to experience kind of the uniform circular motion stuff that we've learned about with the mass spectroscopy. So in this problem then, which gets a little crazy, but we're asked to determine how many revolutions that circular motion will generate in the time it takes to get from one end to the other. So what we're really being asked to determine is the number of revolutions that it undergoes. And so the number of revolutions is going to be equal to the time it takes to travel from one end to the other over the period of its rotational motion. So the question becomes, how do we determine what t is, or period, are in this situation? So let's go ahead and try to tackle that. As I decided to start looking at this one, I thought I'd start with the period side of things to figure out what our period of rotation is. So I know from uniform circular motion that the period is equal to 2 pi times r over the speed that it's moving v, which in this case is the perpendicular component of the velocity. All right, that sounds good, but I don't know r, and I do know v, okay, but I don't know r. So I'm going to see if I can relate this to some of the rotational mechanics that I know are going on. So when it's undergoing uniform circular motion, I know that my net force, mv squared over r, is going to be equal to my force given by the B field that causes the circular motion. So that's going to be, again, the perpendicular component, which we know from the definition of the force due to a B field on a moving charge is going to have a magnitude of q v. In this case, again, it's the perpendicular component of velocity in both cases, multiplied by the magnitude of the B field. So from there, I can, interesting, I can solve for v, so I can find that my perpendicular component of the velocity is going to be equal to q b r over the mass of my electron. So I can plug this in up here, see what happens as we do this. So our period then is equal to 2 pi, I'll leave the r here for now, the m comes on top, divided by q b r. So bonus, look what happens, the r's cancel out, so my period is just going to be 2 pi times the mass, which I know, over q, which I know, times b. All right, well, somewhat helpful, but I don't know what the b is. So I'm going to scroll down here a little bit. So the question is, what is the B field? What is the magnitude of that B field? So I'm going to change colors to make this easier. So the magnitude of the B field is just the B field in a solenoid. And we know from class that the B field in a solenoid is just mu naught times the current, which we know, multiplied by the number of loops over the total length. We're given the number of loops, but we don't know the length. So if I want to substitute this in to my period equation over here, I need to figure out what L is. Well, this is not going super well. I don't even know the time yet, but let's see what happens. Well, the length, we don't know, but we do know that the horizontal, or the parallel component of our velocity, which we can calculate by just taking the velocity given and multiplying by the cosine of the angle. I just noticed my angle here doesn't have a, there we go, it's a theta. So we know that it's going to be a constant velocity in the horizontal direction since the B field isn't going to affect things. So what we find is that, so we need to, or we can take the distance traveled. Since it's a constant velocity in the horizontal direction, we know distance is just going to be equal to the parallel velocity multiplied by t, where t is the total time it takes, right? So the length is just equal to the parallel component of velocity multiplied by the time. We can plug that in to our B equation and watch what happens. I'm going to do all this at once. So our period becomes equal to 2 pi times the mass divided by Q times my B field, which is mu naught times I multiplied by N, and then since it's divided by L, I'll put the components of L up on the top. So we have V parallel times T. And what we find is now we have an equation where we can solve for the thing that we're looking for the entire time. We can solve for T over the period and then get exactly what we're looking for, the number of revolutions that our electron experiences as it travels the length of the solenoid. So I'm going to leave it there, but we know M, we can find V parallel, you know the charge, mu naught, and N and I are all given to you. So I'm going to leave it there and let you guys solve. Tricky problem, but a lot of good stuff. So enjoy and have a box-worthy evening.